Okay, welcome to the lecture number 53. We have been discussing about the gyrostate and we derived the equation of motion, and that was in more of a generalized format. So, today we will take up that generalized rotational dynamics equation and then linearize it to get the gyrostate linearized equation of motion, and that is the equation which is used for the control purpose locally once the system is disturbed from its reference condition or the equilibrium condition. So, from there whatever the small disturbance is there, so that can be controlled using your linear control system. Okay. And also we know as a whole that this whole system is non-linear, and if we want to control the non-linear system, so in that case we have to design the non-linear control, and then we can there is no bound on the disturbance can be as large as possible, and if your control nonlinear control is capable of tackling the problem, then the system can be brought to the reference condition again. So, we start with the our derived equation of motion. So, last time we have worked out so we had here the body in which this is the point O, E1, E2 and E3, there is a gyrostate whose axis is here, and a unit vector is there, either written here in this or this format. Okay. So, here in this case V 0 is the velocity of this point, okay, and P is the linear momentum of the whole system. Okay. So, for this particular case, plus V 0, as we have observed that this linear momentum of the system, if the center of mass of the system is located here, this is the center of mass of the whole system for the whole system. Okay. So, in that case this velocity of the center of mass will be V 0 plus omega cross RCM. If we multiply by m, so that becomes the linear momentum of the system, and as usual this gets reduced to this we have discussed in the last class. So, V 0 cross omega cross RCM, and if point O coincides with the center of mass, let us say this point is, we write this as some point D, center of mass at point D, then RCM will become equal to 0, and therefore, M external gets reduced to your usual form of the rotational dynamics. This we can write with respect to the body frame, means the here the B frame is E1, E2, E3, which is fixed at point O. So, in the case once the O coincide with the center of mass, so this is the situation. Okay. So, this is your the transport theorem in mechanics. Transportation theorem or transport theorem in mechanics. We have derived this earlier also. Okay. So, here in this place H is the total, this is the H total. and that is the total angular momentum. Angular momentum of the system. So, H 0 we have written as m times r center of mass cross V 0. So, obviously, this term will not be present because R C m equal to 0 here. So, this term will drop out and rest we have j double dot omega, where omega is the angular velocity of the frame E 1, E 2, E 3, E 1, E 2, E 3, its angular velocity is omega. And then we have written I s times omega s times E a cap. Okay. So, last time we derived all these things. Okay, and so we proceed from this place and okay, this I do not remember that whether I have done this part or not, but perhaps I have done this. So, for the time being I will assume that this is there, and later on I will come to this issue. Okay, so, our H then gets reduced to E a cap, where E a cap is nothing but the unit vector along the axis of the gyrostate, this rotational wheel. Okay, the wheel which is rotating. So, it is along the its axis, the A vector we have taken. So, A or either we have written as E a cap, this is the unit vector. Okay. So, this is the angular momentum of a gyrostate. If you have such multiple wheels, means say now you have this body, and at the center of mass of this body, this is point O slash center of mass. Okay. So, one wheel you are positioning here in this place, another wheel you are positioning in this place, another wheel you are positioning in this place. Okay. So, this is your wheel. Okay, and for simplicity we can assume that these wheels are located along the 3 body axis. Okay. So, here A was written. So, this A can be assumed like it is a around the E 2 vector or E 3 vector or either E 1 vector. Okay. So, we put 2 other wheels. So, with that this system looks like this. You have the these 3 wheels, and we will assume that this wheel is rotating. Okay. This wheel is rotating right from the beginning, one of the wheel. So, we will assume that the wheel along this is rotating, and we will give a bias momentum to this rotation, we call this as the bias momentum. So, I will come to that later on. Let us look into this equation first. So, if you have this kind of situation where instead of one wheel you have 3 wheels. So, the same equation you will write as H equal to So, what we are doing, this is the angular momentum of the whole body about point O, okay, including the wheels. As such, you just jam the wheels are not rotating. So, this becomes a mass, lumped mass sort of thing. Okay. So, we are considering this to be a rigid body. So, this is very simple equation I time this inertia dyadic for the whole system and dot omega and plus the angular momentum of the wheel at the respective position. So, here this is the wheel number 1. So, it will have the angular momentum along this direction if it is rotating this way. If it is rotating this way, so it will have angular momentum along this direction. So, we can write this as the shape H 1, H W 1, H W 2 and we can write this as H W 3, means these are the angular momentum of the wheel 1, 2 and 3. So, this indicates nothing but H W I summation, okay, I equal to 1 to 3. So, you can see that without much difficulty, once we have got the main equation. So, we got the main equation and we derived this equation for the H and this is for the force. Okay. So, from here easily we have got for the whole system without much trouble. Okay. Now, we can expand the equation. So, we will have dH by dt E equal to dH by dt with respect to the body frame, or here in this case we have the E frame. So, I will write as with E notation, this is with respect to inertial frame and omega cross H. Then insert those values H equal to J double bar omega cross H, which will be so, why we are converting it from the inertial frame to the body frame? This is in the inertial frame and this is with respect to the body frame. Okay. Reason is very simple, that the omega that you measure, it is a directly measurable in the inertial space. Sitting on the earth, we do not measure the angular velocity of the satellite. The instruments are on board the satellite and those instruments, the red gyros, they are measuring the angular velocity of the satellite. So, it is a natural to describe this kind of system in the body frame itself in terms of body frame. So, this is your M external, the torque acting on the system. Okay. So, the right hand side, now in the body frame, this differentiation is with respect to the body frame. Therefore, in the body frame, the inertia this inertia term, it will not change, and then we can write this as plus we can pick up the term from this place and write here omega cross J double bar dot omega, we club it together and then the other terms we can write as d by dt this is with respect to small e. Now, you can see that this part this as usual, this is your the normal. If while we work with the rigid body dynamics, so we derived this equation m external, what we have written as the Euler's dynamical equation, m external equal to G plus omega cross, this we derived. Okay. The same thing we have written in other format also, like instead of writing in terms of the inertia dyadic, we can write in terms of the inertia matrix, and there we have written it like this times omega tilde cross times j times omega tilde. Okay. So, what is the what we can see that this term is extra addition, this is the extra term appearing due to Wills. Okay. This term is as usual the external torque applied on the system, and this is your basic Euler's dynamical equation. So, this this part, this is your extra part. Okay. So, now we need to, we have done this part, we need to work out this part. Okay. So, d by dt we can do it on the next page. Summation omega cross H W. Here this term is separate, we should remove this part, and this part is here written separately. This term is separate, this term is separate, this is one term and this is one term. So, we have this term here, and the other term is omega cross H W I. So, this is omega cross omega cross H W I, and I is from 1 to 3. So, this is the term that we need to work out. Now, H W I, this term we need to expand and look into. Okay. So, if you look here in this part, here in this place. So, I s times omega s times E a cap, if it is along the first direction. So, instead of writing here E a cap, I can replace this as E 1 cap, okay. And this is along the first direction. So, first direction spin along the first direction, like this we can write, and this is the term which we have written as H 1, okay. And H 1 multiplied by E 1 cap we are writing as H 1, or we have given this notation H W 1, because this is for the will, this is H W 1, W stands for the will. Okay. So, following this notation, we should understand that here H W I, this is nothing but I W times or I s times omega s times, depending on the direction, E I cap. this is your h w I. Okay. So, once we differentiate this quantity here, so we pick up this and we have to calculate this, expand this quantity. So, this quantity if we expand it, so you can see that h w I can be written as h 1, and let us name this quantity for, this is for the ith wheel. So, we will name this as h 1 times E 1 cap for the first wheel, h 2 times E 2 cap for the second wheel, h 3 times E 3 cap for the third wheel. So, this is for the first wheel, for the second wheel and for the third wheel. So, following that notation, so this becomes h 1 E 1 cap, and this differentiation stands with respect to the body axis, okay, h 2 times E 2 cap omega cross this summation of the all the terms. So, summation h w I, let us write for the time being like this. So, now we have to look into this place. So, obviously, in the body frame this E 1 is not changing. Okay. If you are looking taking derivation, this is E 1, E 2 and E 3, and if you are taking the derivative of this term with respect to this frame itself. So, in this frame h 1 will change. So, we will get h 1 dot E 1 cap plus h 2 dot E 2 cap plus h 3 dot E 3 cap. However, your E 1, E 2, E 3, these are the fixed vector in this frame, okay, and this basically these are the unit vectors. So, these vectors are not changing with time. So, we need not take the derivative of this, but if the same thing we are doing with respect to the inertial frame. So, we have to take that term like writing omega cross h, okay, that extra term appears if it is with respect to capital E, but here in this case this will not appear because this is with respect to the body frame. So, this quantity plus omega cross this quantity which is h 1 plus h 2 plus h 3, all these are for wheels, h 2 these are for the wheels. I have missed here. So, omega 1, omega 2, this is h wheel 3, all these places h w 1, h w 2, h w 3. Carrying this subscript it is a little difficult, but for clarity I am putting it here. Okay. So, all these terms can now be combined. Now, as I told you in the beginning that we also put some bias momentum. Okay. So, bias momentum, I told that this wheel will be given a bias momentum, and let us say that bias momentum is given in the negative direction of S 2 E 2. So, that will be negative direction of this one. So, that will point here in this direction. So, this is H 0 E 2 with minus sign, this becomes. Suppose this is the bias, means these are not rotating, at that time this is rotating, and this is rotating here in the opposite direction, H 0 minus E 2. Already I have written this plus minus, if you remember that I have written there the bias momentum as plus minus H 0 times the corresponding the unit vector in that direction. So, here I am assuming that it is only pointing toward the negative direction of the E 2. Okay. So, if we do that, so in that case we will have one more term here in this place which will appear as minus H 0 times E 2 cap, and this is associated with this wheel. So, right in the beginning your wheels are suppose not rotating, only this wheel is rotating, and that is having the angular momentum H 0 E 2 with respect to the body axis. So, this is with respect to the body axis system. Then for if the satellite is getting diverted from its equilibrium state or the reference state because of the external disturbance. So, you will speed up these wheels, this one wheel, this is the second one, and this is the third one. Okay. So, as you speed up, so these terms will then appear, all these three terms will appear, and this modifies your equation of motion. Okay. So, once we now combine all the terms, so what we have written that m external this equal to j dot times omega dot plus omega cross j double dot j times j dot omega. Okay. This was the basic term involved, and thereafter this term is there which we have now expanded. So, this expanded term we can put here from this place, this becomes H W 1 dot E 1 cap plus H W 2 times E 2 cap E 3 cap and plus omega cross this quantity here, which is H W 1 times E 1 cap H W 2 times E 2 cap plus H W 3 times E 3 cap minus H 0 E 2 cap. And then we can get the terms separated out along the three body axis. This is along the first body axis, this is along the second body axis, and along the third body axis. So, here what we will assume that j double bar, it is equivalent of the matrix notation. This we will write as I 1, I 2, I 3, assuming that the other terms are 0, the off diagonal terms are 0, or either maybe for better presentation we can keep this as j 1, j 2 and this as j 3. So, indicating it is a diagonal matrix. Okay. So, we will have here M external in matrix notation M 1, M 2 and M 3, and this we can write as follows. So, the first term basically we can separate out like this, and we can work out all the terms separately. So, the first term it appears from here this times omega dot. So, the first term will be j 1 times omega 1 dot plus and if you remember from your attitude dynamics. So, this part will simply break up as minus this, writing in a cyclic way I 2 minus I 3. So, this is the part from this place to this place. Thereafter, we have to use this. So, that part goes as so, we write here separately this and plus H 1 dot, which is appearing from this particular one, this is corresponding to the E1 direction, and then from this place we have to work out the corresponding value. So, this we need to do. Okay. Similarly, the other part will be J 2 times omega 2 dot minus omega 3 omega 1 I 1 I 3 minus I 1 plus H 2 dot and plus other terms that we need to write. Similarly, this will be omega 3 dot minus omega 1 omega 2 times omega 1 minus omega 2. Okay. This is the easy way of remembering this, as I have told you earlier, this is H 3 dot. Now, rest of the terms we need to insert here in this place whatever they are. So, those terms are related to your omega cross this. Okay. So, omega cross here H 1 or H 1 times E 1 cap or H w 1 times E 1 cap, H w 2 times E 2 cap and H w 3 times E 3 cap minus H 0 times E 2 cap. So, these two terms will be combined together, and if we combine, so we can write this as. So, we are looking at this term, the second term, this is the second term in the previous equation. Okay. So, this term then it can be reduced to omega cross, already you know that this will be written as minus omega 3, then omega 2, omega 3 0, this will form this Q symmetric matrix minus omega 1 minus omega 2 omega 1 and then 0 here in this place, and this will operate on this vector. So, this vector is H w 1, then H w 2 minus H 0 and H w 3. Okay. So, this part is equivalent to this in the matrix format. Okay. So, from this place it is easy to write it like this, and therefore, I am writing this way. So, this becomes equal to minus omega 3 times H w 2 minus H 0 plus omega 2 times H w 3. Okay. The second term will be omega 3 times H w 1 minus omega 1 times H w 3 okay, and then the last term will be minus omega 2 times H w 1 then plus w 1 times H w 2 minus H 0. So, these are the three terms, and these three terms will appear in this place, and we can write them as this term we can write first omega 2 H w 3 minus the other this term, then we can pick up this particular term. Okay. So, that becomes minus omega 3 times H w 2 minus H 0. Okay. So, this completes the external torque along the first direction. Similarly, the other term I can take up, which is omega 3 times H w 1, omega 3 times H w 1 and minus omega 1 times H w 3. So, you can see that the sequence here for omega 1 you had here omega 2 and this is omega 3. So, same way here it is appearing omega 2 omega 3 and there is a minus sign here, and the corresponding term H term gets exchanged, omega H w omega 3 comes here and H w omega H w 2 goes here and H w 3 comes here in this place, and this is the only extra term which is due to the bias momentum which is appearing here in this place. Okay. So, similarly, the third term we can pick up. So, here first term is omega 1. So, we will pick up this and write here omega 1 times h w 2 minus h 0 and then minus omega 2 times h w 1. So, these are the three equations and this is a nonlinear equation. Okay. So, three equations for the gyrostat. So, how many degree of freedom this system has? This system has 3 plus 3 total 6 degree of freedom. Why? See, if your point O is not coinciding with the center of mass of the system, then this translational motion for this enters into the equation through V cross P. Okay. So, 3 becomes for translational, which has got deleted because of the center of mass coincide with the point O. So, this will get dropped out. So, rest we are left with then the 3 rotational dynamics equation for the main body. Okay. So, 3 degree of freedom for the main body of this satellite and 3 degree of freedom for the 3 wheels. Okay. So, total 3 into 3 total 6 degree of freedom system this is. Okay. So, here in this case if the gyrostat, if this gyrostat has only one wheel. So, in that case this 3 will be replaced by 1, means then it becomes 3 plus 1 a total 4 degree of freedom system, but here currently this is 6 degree of freedom system. Okay. So, we have completed this equation of motion and okay, next we can discuss about the linearization. So, that we will do in the next lecture. So, we will continue in the next lecture. Thank you very much.